All right, this is question number 4 from 2011. Right, we have our graph. We're told g of x, and we got this little addition to it here with the integral. G of x has an integral in it. We want to find g of -3. We want to find the derivative of that. Remember, this notation that we just mentioned right here is basically saying that f of x is the derivative of g of x. That's what that part is. But don't forget this first part that we have there, okay? All right, so that's what that is telling us. We're going to find when it has maximums, points of inflection, and then we're looking for the average rate of change here. We want the average rate of change part here. So we got to be worrying about that language a little bit. And it is talking about the mean value theorem here. Okay? All right, well, let's get started on this. So the first part here just says if this is g of x, find g of -3. So g of -3 is just going to be 2 times -3. We're going to put in -3 wherever we see these x's. We're going to go from 0 to -3 of f of t dt. F of t just being this graph. This is the graph of f. It's a little cut off there. All right, let's keep going with a little bit of this. The first part here, that was pretty straightforward. That's -6. But here we have our endpoints kind of look backwards, right? We go from 0 to -3. So we're going to have to flip that around. We got to flip this around. And we said when we do that, we have to make the whole thing negative. So we're going to subtract from -3 to 0 of f of t dt. Now, once again, just know what it is we're talking about. This is just the area. That is the area under the curve from -3 to 0. So we're talking about this kind of quarter of a circle. So let's look at that quarter of a circle. A circle is pi r squared. This radius here is 3. So this becomes pi times 3 squared, so 9 pi, but this is only a quarter of that circle, so we have to divide by 4. So my final answer, I have -6. I'm going to subtract 9 pi divided by 4. So we're going to have that set up right there. Now we could go farther with that. If this is a calculator section, we can punch that into our calculator. If you do that, if you punch this all into your calculator, you're going to get -13.069. Always a good idea, 3 decimal places. Hopefully they'll tell us that in the question as we go. Okay, let's keep going. We're going to find g prime of x and then g prime of -3. Okay, so I'm just going to switch colors here, and we're going to find g prime of x. Well, if g of x is 2x, well, the derivative of 2x is 2, plus we need this part, and we just said the derivative of the integral is just that function, so that just becomes f of t. So the derivative of g of x is 2 plus f of t. So when we want the derivative evaluated at -3, we get the 2, and we need f at -3. So if I go up here, f of -3 is just that point right there. It's actually 0. So that whole thing is just 0. So 2 plus 0 is 2. So g of -3 was this whole thing. There's my derivative. There's g prime of -3. Okay, let's keep going. Part B. We have our same graph. Now with part B, we want to determine the x-coordinate of the point at which g has an absolute maximum. Okay, so absolute maximum. Well, remember, for maximums, the maximums occur when the derivative is equal to 0. So we just found the derivative, so let's use that. We said g plus f of t is the derivative. We want that equal to 0. Well, that's going to equal 0 when f of t is equal to -2. So there's negative 2. When does f of t equal negative 2? Well, this point right there. So really it's just finding what that point is. What that point is. So we need the equation of this line. We can find the equation of this line and set it equal to negative 2. So I'm going to go ahead and do that. You can do it a number of different ways to figure out that equation. Some of you may use the endpoints you can figure out. You can do rise over run, the slope, the whatever you can do to figure out the equation of that line. So I'm going to use y equals mx plus b. Let's figure out my slope. Well, my slope, to go from there to there, I went down 6 and over 3. So my slope is actually negative 2. And that is my y-intercept at 3. So there's the equation of the line. So let's set that equal to negative 2 and solve for x. So I'm going to move that over. That becomes negative 5. And I'm going to divide off that negative 2. And x equals 5 halves is the only point where my derivative is equal to 0. And if we go ahead and look at this and say g prime, we'll see whatever g is, there's 5 halves. So let's try something here. And remember, there was our function for g prime. So if I put something like 0 in here just to test it, 2 plus f of 0 is 3, that becomes a positive number, and we're going up. Let's try negative 3. So I'm going to try this point here. F of negative 3 is, f of 3, is negative 3. So this is f of 3 is negative 3. So if 2 plus negative 3 is actually a negative, and in fact, that is a maximum. All right, part C. Find all the values for which g has a point of inflection. Okay, so now we want a point of inflection. Well, we said our point of inflections are when the second derivative is equal to 0. The second derivative is equal to 0. Well, if the derivative of x is f, then the second derivative of x would be f prime. We want the f prime of x. And we want to know when is that equal to 0. So we want that equal to 0. Well, let's look at that second part here. This one is really just analysis here. So when f prime is equal to 0, there's f is this graph here. So when f prime is equal to 0, we have a maximum value. Well, that's kind of the only maximum value we have here. We could assume maybe this is a minimum and a maximum, so we can try those endpoints. But the big one here is 0. I got to test 0. So if we look before 0, what is happening? Well, f is increasing. Okay, so f is increasing. We're actually going to set up kind of our 3 setup here. So I have the double prime, which is f prime. We have g prime, which is really f. And then we have g up here. So f is increasing. That means its derivative must be positive. And if we go all the way back up here, that means this is concave up. Now after this, we're decreasing all the way down. So f is decreasing. That means its derivative must be negative. And if we go all the way back up here, that is concave down. So we have a point of inflection at x equal to 0. Now we can't tell what is happening out here at negative 4. We know it's increasing here, but we really don't know what the graph looked like over on this side. Same thing down here. It's decreasing to that point, but we don't know what happens after. So we can't call that a point of inflection. All right, one more part here. D, find the average rate of change. So that's the key here. We are looking for the average rate of change of f. A lot of people will look at that and they'll see average and start thinking that this is our average of a function idea, a to b, f of t dt. That is the average of the function, but we want the average rate of change. Well, rate of change is just slope. So they're saying, what is the average slope of this whole curve here? Well, we don't find the slopes at all the points and then add them together. That's not the way average slope works. Think back to your physics. An average slope is going to be the slope of the line from the start to the finish. So if we just connect those dots right there, we can find the slope of this line. That becomes the average slope of the whole curve. So this was at -1. We're going to go down 2 to get to -3. And then we got to go all the way. What's our run here? Well, we're at -4. We're all the way to 3. So our run is 7. So our average slope, our average rate of change, is -2 over 7. Now the other part of this says there is no point C for which f prime c, which is really what we found here, we found f prime, the slope, is equal to the average rate of change. Explain why this statement does not contradict the mean value theorem. So we went through some questions in class where we found the average rate of change, we found f prime, and then we actually found c, right? Because the equation, if we go back up here, said that this is f of c times b minus a. And that's the way the equation worked here. And we then tried to figure out what c was. There is no c value here, and it doesn't contradict the mean value theorem because the mean value theorem has a couple of points. The mean value theorem says our graph must be continuous and it must be differentiable. Well, it is continuous. If we look at our graph, it is continuous all the way through. But at that point right up here at f of 0, we are not differentiable. We have this point, a cusp. We have this quick change here where there is no derivative. There is not a single tangent line at that point. It is not differentiable at f of 0. So in fact, the mean value theorem doesn't apply to this at all. That's why it doesn't contradict it. All right. Good question. Keep practicing. We got about a week before our exam.